Quantum computing: need, present, and future. Imagine a computer that can solve in minutes a problem that would take today's fastest supercomputer thousands of years. This isn't science fiction, it's the promise of quantum computing. Quantum computers harness the laws of quantum mechanics to tackle problems beyond the reach of even the most powerful classical machines. Hello and welcome. In Elemental Science magazine, we'll explore why quantum computing is needed, what the current state of the technology is, how quantum cryptography is poised to change cybersecurity, and what's next. The goal is to educate and spark your interest in this cutting-edge field. A 2019 quantum experiment solved a task in minutes that a classical supercomputer would take millennia to finish, hinting at a new era of computing. What is quantum computing? It's a new paradigm using quantum physics, superposition, entanglement, to process information in ways classical bits cannot. In simple terms, while classical bits are 0 or 1, quantum bits, qubits, can be both 0 and 1 at the same time, enabling exponentially more parallel computations. The need for quantum computing. 3. Why do we even need a new form of computing? The answer lies in the limitations of classical computers and the daunting problems they struggle to solve. Moore's law is slowing. For decades, computing power grew exponentially as we crammed more transistors onto chips. Now we're hitting physical limits. Transistors are approaching atomic scales, and issues like heat dissipation and quantum tunneling are causing progress to plateau. Classical computing is nearing a saturation point, beyond which simply adding more transistors won't give the leaps we need. This end of Moore's law drives the search for a new paradigm of computing. Computational bottlenecks. Certain classes of problems are intractable for classical computers. Examples include chemical and material simulation. Accurately simulating molecules, proteins, or new materials at the quantum level is extremely complex. Even today's supercomputers struggle with these calculations, which are crucial for drug discovery and new materials development. Quantum computers, by working natively with quantum states, could model these systems much more efficiently. Optimization problems. Complex optimization, logistics, scheduling, portfolio optimization can have astronomical combinations to search through. Classical algorithms often can't find the best solution in reasonable time when the problem size grows. Quantum algorithms, like Grover's search, promise speed-ups for exploring large solution spaces. Cryptography and number crunching. Some mathematical problems, like factoring very large numbers, which underlies RSA encryption, are practically impossible for classical computers. They'd take billions of years in brute force time. But a quantum algorithm, Shor's algorithm, could crack such problems in a feasible time if a large quantum computer existed. Quantum advantage. Quantum computing offers a way around these bottlenecks. By leveraging superposition and entanglement, a quantum computer can explore many possible solutions simultaneously instead of one by one. In theory, this means certain tasks might be done exponentially faster than on a classical computer. For example, a quantum computer might solve in hours a problem that would take a classical computer thousands of years. This speedup isn't for every computation, but for specific problem types, it can be game-changing. Real-world impact. The need is ultimately driven by real-world demands. We have insatiable hunger for processing power in areas like AI, climate modeling, and big data analytics. If classical systems can't keep up due to fundamental limits, quantum offers a path forward. Imagine more accurate climate predictions by simulating atmospheric chemistry in detail, or discovering new pharmaceuticals by efficiently analyzing molecular interactions. These are the kinds of breakthroughs we hope quantum computing will enable in the future. In this video, we've highlighted that classical computing can't infinitely improve due to physical and computational limits. quantum computing is needed because it operates on completely new principles that bypass some of these limits, allowing us to tackle problems that were once thought impossible to solve in practice. As one IBM definition puts it, quantum computers will tackle problems too complex for classical computers, a crucial need as our technological demands grow. Now that we know why quantum computing is important, let's examine where we are today. How far along is this technology? Who are the major players? And what milestones have been achieved so far? Today's quantum computers are still in an early stage, often called NESC, noisy intermediate-scale quantum devices. They have tens to a few hundred qubits, and those qubits are prone to errors, noise. Different technologies are competing. Superconducting qubits, used by IBM, Google, Rigetti, trapped ion qubits, IonQ, Quantinuum, photonic qubits, Xanadu, PsiQuantum, and others. IBM has been a leader, making steady progress in qubit count and quality. In 2021, IBM unveiled a 127-qubit processor, codenamed Eagle, followed by a 433-qubit Osprey in 2022. In 2023, IBM broke the 1,000-qubit barrier with IBM Condor, a 1,121-qubit quantum processor, a record for qubit count at the time. This was a major scaling milestone, pushing quantum chip design to new levels of complexity. Condor packs 50% more qubits per area than its predecessor. It's important to note that having more qubits doesn't automatically mean a useful computer. Quality and error rates matter. But scaling up is a critical step. Google famously demonstrated quantum supremacy in 2019 with a 53-qubit superconducting chip, Sycamore. Their quantum computer performed a carefully chosen random number sampling task in about 200 seconds, a task they estimated would take a classical supercomputer thousands of years. It was a landmark moment showing a quantum device beating a classical one at something. Since then, Google has focused on improving qubit quality and error correction. In 2023, they demonstrated the first prototype of a logical qubit. By arranging 49 physical qubits in a surface code, they could detect and correct certain errors, a key step toward fault-tolerant computing. This showed that increasing the number of qubits in an error-correcting scheme reduced the error rate, which is a big research milestone on the road to stable quantum computers. Startups and other players. It's not just tech giants. IonQ, a startup using trapped ion technology, has built systems with high-fidelity qubits, fewer in number, but very low error rates per operation. Rigetti Computing works on superconducting qubits and integrates quantum processors with classical systems. D-Wave Systems, a Canadian company, has taken a different approach with quantum annealers, specialized quantum machines for optimization problems. D-Wave's latest Advantage 2 annealer has over 5,000 qubits, though of a different kind. Quantum bits used in a manner akin to an analog solver rather than general quantum logic gates. In fact, in 2023-2025, D-Wave showed its annealing quantum computer could simulate certain magnetic materials in minutes, a task that would take a classical supercomputer an estimated million years, and impractical energy to solve. This was touted as the first quantum supremacy for a useful real-world problem, specifically in materials science, using an annealing processor. Software and ecosystem. On the software side, there's been significant development of tools and languages to program quantum computers. For example, IBM's Qiskit and Google's Cirq are open-source frameworks that let developers write quantum algorithms. Microsoft offers QBurst as part of its quantum development kit. There are also cloud services. IBM Quantum provides cloud access to their hardware. Anyone can run small experiments on IBM's quantum processors via the cloud. And Amazon Braket and Microsoft Azure Quantum allow access to various quantum hardware from IonQ, Rigetti, D-Wave, etc. through their cloud platforms. This cloud accessibility is important. It's training a generation of developers in quantum programming and integrating quantum and classical computing workflows. Major achievements. so far. Aside from the headline of quantum supremacy, there have been other notable milestones. Researchers have run small instances of quantum algorithms like Grover's and Shor's on actual hardware. Shor's algorithm was demonstrated factorizing small numbers like 21^37 on early devices, a far cry from breaking RSA, but a proof of concept. In 2020 and 2021, quantum machines achieved quantum advantage in specialized tasks, e.g., a photonic quantum computer in China, USTC's experiment, performed boson sampling, a complex photonics calculation, faster than any classical method, marking another kind of supremacy claim in a narrow task. Quantum volume, IBM's metric combining qubit count and fidelity, has been steadily improving, doubling almost yearly, indicating overall progress in making qubits more usable. Industry and academic involvement. Multiple countries and research labs have built quantum processors. For instance, in 2023, Japan installed its first domestically operated quantum computer, an IBM system, for researchers. Europe and China have large government-funded programs, spurring a global quantum race. Collaboration is key. Many advances, like error correction codes and new algorithms, are coming from academia partnering with companies worldwide. Current limitations. It's worth noting that today's quantum computers are not yet outperforming classical computers on practical everyday tasks, outside of those contrived demonstrations. They are experimental and often error-prone. Qubits lose their quantum state quickly, a phenomenon called decoherence, and operations are probabilistic, meaning results have noise and need statistical averaging. We're in the phase of learning how to scale up qubits and stabilize them through error correction. Quantum computing is no longer just theory. Real machines exist and are improving rapidly, but they are still limited. IBM and Google have paved the way with superconducting qubit systems, achieving over 1,000 qubits in IBM's case, and demonstrating key concepts like quantum advantage and error correction in Google's case. Startups and other companies add diversity with different technologies, and even claims of useful quantum supremacy in niche areas, like D-Wave and optimization. The ecosystem now includes robust software tools and cloud platforms, meaning you, as a tech professional, can actually experiment with quantum code on real hardware. We're at an exciting inflection point. Quantum computing is moving from laboratory curiosity toward an emerging industry. One field where quantum technologies have immediate implications is cryptography. What it is, why it matters, and how it could overhaul cybersecurity. The threat quantum computing poses to encryption. Modern cybersecurity heavily relies on cryptographic algorithms that are tough for classical computers to break. For example, RSA encryption, used in secure websites, banking, etc., depends on the fact that it's astronomically hard for a classical computer to factor a huge number into primes. It would literally take a classical supercomputer on the order of thousands or even billions of years to brute force such encryption. However, a powerful enough quantum computer could crack these codes in a much shorter time, perhaps minutes or hours, using quantum algorithms like Shor's. This is often called the quantum threat to classical cryptography. In other words, once fully functional quantum computers emerge, much of our current encryption, RSA, ECC, even some AES, could become vulnerable. Everything from private emails to state secrets would be at risk if intercepted by someone with a quantum computer. This is a big deal for cybersecurity. What is quantum cryptography? Quantum cryptography, also known as quantum encryption, refers to securing data using the principles of quantum physics, rather than relying solely on mathematical complexity. The most well-known example is quantum key distribution, QKD. QKD uses quantum particles, typically photons, to distribute encryption keys between two parties with provable security. The magic here is that by the laws of physics, any eavesdropper trying to intercept the key will unavoidably disturb the quantum states, alerting the legitimate parties to foul play. In simple terms, if Alice and Bob use QKD to generate a shared secret key, they can detect if Eve, an eavesdropper, looked at the photons. If the line is clean, they now have a secret key that no one else knows, which they can use for traditional encrypted communication. Unlike current encryption, whose security rests on unproven math problems, QKD's security rests on fundamental physics. If done right, it's theoretically unhackable. Why it matters for cybersecurity. The rise of quantum computing creates an urgency to upgrade our security. Quantum cryptography methods, like QKD, use quantum tech itself to secure communications. QKD is already a reality in niche applications. For instance, banks and government labs have tested QKD links for transmitting ultra-secure data. Some financial institutions use QKD for interbank communication. In one notable achievement, scientists in China demonstrated intercontinental QKD between Asia and Europe using the Metis quantum satellite, distributing quantum encrypted keys between China and Austria, 7,600 km apart. This laid the groundwork for a future global quantum secure network. The promise is communications that even a quantum computer can't eavesdrop on, because any interception is detectable. However, QKD and similar technologies face practical challenges. They often require specialized fiber optic lines or satellites, and distance is limited. Direct fiber QKD works up to a few hundred kilometers due to photon loss. We're seeing progress with quantum repeaters and satellite relays to extend this range. Post-quantum cryptography, PQC, developed new classical algorithms that are resistant to quantum attacks. This is a parallel effort in the cryptographic community. Rather than using quantum physics, PQC relies on alternative hard math problems, lattice-based cryptography, hash-based, etc., that even quantum algorithms are not known to solve efficiently. IBM.com. In July 2022, the U.S. National Institute of Standards and Technology, NIST, announced a set of new encryption algorithms to replace RSA-ECC, specifically designed to withstand quantum attacks. Companies like IBM are already integrating quantum-safe encryption. For example, IBM's Z systems now implement lattice-based cryptography for security. This is crucial for a transition period. We need to start adopting quantum-resistant encryption before quantum computers become powerful, because of a concept called harvest now, decrypt later. This means an adversary could record sensitive encrypted data today and simply store it. Years later, if they have a quantum computer, they could decrypt that old data if it was protected with legacy algorithms. Certain secrets, think government or personal health records, remain valuable for decades, so we can't wait until quantum computers arrive to act. We have to upgrade encryption in advance. Quantum cryptography. Today, as of now, 2025, QKD has been demonstrated in various real-world settings. Bank-to-bank communications in Switzerland, secure government links, and even metropolitan QKD networks. However, it's not mainstream due to cost and infrastructure requirements. Meanwhile, the cybersecurity industry is gearing up for PQC. Many organizations are inventorying their cryptographic systems and planning migration to quantum-safe algorithms, sometimes called crypto agility. Governments have issued directives, e.g., US NSA recommends transitioning to quantum-resistant encryption by the mid-2030s. This is a direct response to the understanding that within the next decade or two, quantum computers could become a threat if we're not prepared. Experts estimate that a cryptographically relevant quantum computer, one able to break RSA 2048, might be still a decade or more away, but opinions vary from 5 years to 20 years for that possibility. The prudent approach is to act now, given the long lead times to transition global infrastructure to new cryptography. Impacts on cybersecurity. The coming of quantum computing is both a threat and a catalyst for security innovation. On one hand, adversaries with quantum capabilities could undermine the foundations of digital security, which would be a disaster for trust in everything from banking transactions to encrypted messaging. On the other hand, quantum technologies provide new tools, like QKD, to achieve security levels impossible with classical means. We are likely to see a period where organizations deploy hybrid solutions. For example, combining classical post-quantum algorithms with QKD for high-stakes links. Cybersecurity professionals today need to be aware of this coming shift. Quantum readiness is becoming a theme, ensuring your encrypted data won't all suddenly become readable by 2030 because you failed to plan. Quantum computing forces us to rethink how we secure information. Quantum cryptography offers new methods to protect data by using physics itself as the guarantee of security, and is already enabling ultra-secure communication channels. Simultaneously, the specter of quantum-powered code breaking has kicked off a global race to deploy quantum-resistant encryption before it's too late. For tech professionals, this means staying informed about evolving security standards. In summary, quantum technology is both the villain, threatening our current cryptographic systems, and the hero, providing next-generation tools to secure our digital world. It's a fascinating interplay, and one of the most important reasons to follow developments in quantum computing. What's next for quantum computing in the next 5 to 10 years? Let's shift our focus to the road ahead. Upcoming advances, open challenges, and industry predictions. Scaling up and error. Correction. The foremost challenge and goal is scaling quantum computers to a size and reliability where they can solve useful, real-world problems better than classical computers. This is often dubbed quantum advantage or the Holy Grail, fault-tolerant quantum computing. In the next decade, expect qubit counts to continue rising into the thousands. But even more importantly, expect breakthroughs in making qubits more stable. All major players have roadmaps targeting a functional large-scale quantum system by the end of the 2020s. For instance, Google announced an aim to build a useful, error-corrected quantum computer by 2029. Similarly, IBM has laid out a detailed path to a large-scale fault-tolerant machine by 2029. Achieving this will require successful error correction, turning many physical qubits into one high-quality logical qubit. We might see the first logical qubits, with longer coherence times than any physical qubit, demonstrated in the next few years. In fact, by 2025, some prototypes of logical qubits have already been shown on small scales. As mentioned, Google's 49-qubit error-correcting array. By 2030, the goal is to have enough logical qubits to perform meaningful computations like breaking certain cryptographic keys or simulating complex molecules that classical computers cannot handle. Near-term applications and hybrid computing. In the 5-10-year horizon, we expect quantum computers to work alongside classical computers rather than replace them. The term quantum accelerators is apt. Quantum processors may serve as specialized coprocessors accessed via the cloud for particular tasks, much like GPUs accelerate graphics.ml tasks today. Industries likely to see early benefits include pharmaceuticals and chemistry, using quantum simulations to find new drug molecules or optimize chemical reactions. Even a small quantum computer can potentially simulate small proteins or catalysts more accurately than classical methods. Finance. Optimizing portfolios, risk analysis, and Monte Carlo simulations could get speed-ups from quantum algorithms. There's heavy R&D in this area. Many banks have quantum research teams now. Logistics and manufacturing. Solving complex routing problems or optimizing supply chains via quantum annealing or hybrid algorithms could yield improvements in efficiency and cost. Materials. Science. Designing new materials, e.g., better batteries, or superconductors by simulating atomic interactions with quantum computers. These applications will likely start as research experiments in the next few years and, as hardware improves, could transition to commercial use. We might see the first commercial quantum computing services achieving a genuine advantage for specific tasks by late 2020s. Quantum plus AI. Another exciting frontier is the intersection of quantum computing and artificial intelligence. Researchers are exploring quantum machine learning algorithms. Could a quantum computer accelerate training of certain models or find patterns in data more efficiently? It's early days, but companies like NVIDIA are even working on integrating quantum with classical HPC for AI. By 2030, we might have hybrid workflows where parts of an AI computation are offloaded to a quantum chip for a speed boost or improved optimization. Quantum networks and the quantum internet. Looking ahead, it's not just computers, but networks of quantum devices. There is work on the quantum internet, a network that uses quantum signals, photons, to connect quantum processors and enable secure communications, using entanglement distribution for QKD, for example. In 5 to 10 years, we expect the first rudimentary quantum networks connecting cities or research centers. Europe, the US, and China all have quantum communication network initiatives underway. This ties back to cryptography. A quantum internet could ultimately enable secure communications worldwide, as well as distributed quantum computing, small quantum computers linking together to tackle a problem. Industry growth and investment. From a business perspective, the quantum computing industry is poised for massive growth. Estimates vary, but multiple analyses foresee a multi-billion-dollar market by 2030. For instance, one forecast suggests the market will grow from around $1 billion in 2024 to over $20 billion by 2030. In the longer term, McKinsey projected that by 2035, quantum could be a $1.3 trillion industry in terms of value created. Practically, this means more startups, more jobs, and more resources pouring into quantum R&D. Tech professionals might find new career paths as quantum algorithm developers, quantum hardware engineers, or quantum cryptographers. Companies that start exploring quantum solutions early could gain a competitive edge if and when quantum advantage for their domain arrives. Open challenges. It's not all rosy. Significant hurdles remain. Decoherence and error rates are the perennial challenge. Finding better qubit designs, like topological qubits, which firms like Microsoft pursue, though these are still not realized, could be a game changer if successful. Scaling also bumps into engineering issues. Controlling thousands or millions of qubits means dealing with complex cooling systems. Many quantum chips must be at millikelvin temperatures, wiring and readout electronics, essentially quantum engineering on a systems level. There's also the challenge of software and talent. Writing quantum algorithms is hard, and there's a shortage of people with the cross-disciplinary expertise, physics, computer science, math, to drive innovation here. The next decade will likely see a big push in quantum education and workforce development to fill this gap. In summary, while the trajectory is promising, success is not guaranteed. We're trying to harness very delicate quantum effects, and unexpected roadblocks could appear. But so far, progress has been steady and even accelerating. Predictions: next 5 to 10 years. By 2030, we expect to have quantum computers with perhaps hundreds of logical qubits or tens of thousands of physical qubits if roadmaps stay on track. They may not yet be general purpose, but they should be capable of outperforming classical supercomputers in certain areas consistently, moving from one-off demonstrations to practical tasks. We'll likely see at least 1 or 2 quantum advantage applications where companies use a quantum computer to do something economically useful that saves time or money compared to classical computing. The field will probably consolidate. Perhaps a few leading hardware platforms will emerge as standards, similar to how GPU makers consolidated. And importantly, many more enterprises will become quantum aware. Just as AI went from niche to mainstream over a decade, quantum could be on a similar trajectory now. Gartner even included quantum computing in its hype cycle, predicting a turning point in a few years for broad adoption planning. Quantum computing is a once-in-a-generation technological shift, from the binary world of bits to the strange exponential world of qubits. In this video, we covered why it's needed, classical limits, and big unsolved problems. The current state, rapid progress by IBM, Google, and others, though challenges remain, and dove into quantum cryptography, illustrating how quantum tech will both disrupt and enhance cybersecurity. We also peered into the future, anticipating significant advances in the coming decade, from scaled-up hardware to real-world applications and a new quantum-ready security landscape. Takeaways: quantum computing holds immense promise, from revolutionizing drug discovery and materials science to rendering current encryption obsolete, and driving us to invent new safeguards. Today's devices are early prototypes, but they're improving fast. Major companies and startups are pouring in resources, and governments worldwide treat this as a strategic priority. For tech professionals, now is the time to learn the basics of quantum computing. Even if you're not a physicist, understanding quantum algorithms and quantum-safe security will likely become part of the advanced IT toolkit. In short, quantum computing is moving from theory to reality. Its need is clear, its present is here, albeit nascent, and its future is bright, albeit challenging. It's an exciting field where each year brings new breakthroughs, so keep watching this space. Who knows? In a decade, we might be having another discussion about how quantum computers have become just another cloud service we all use under the hood. Thanks for watching. Subscribe to Elemental Science Magazine.